Hi, my name is Sanghun Alex Lee, or Alex, and my project is the optimization of a Morcellation bristle density experiment. Disclaimer, I had originally intended to do my project on optimizing the angle of insertion for a arterial venous graft through computational fluid dynamics software. This would have been accomplished by modeling the artery and the vein, and then modeling a connecting graft, and varying the angles in a CFD software, and seeing at which angle we would find the optimal flow rates, diversion flows, and et cetera, low rates of stagnation and such. Unfortunately, a master's student I was working with in the lab decided to write his thesis on the very same subject, and I decided that submitting two papers on the same subject would have been iffy at best and cheating at worst, so I decided to change my project to a different subject. After consulting with Professor Jakila, we landed on the optimization of this experiment. So, background. Morcellators are kind of like pipe cleaners, and they're used to excite and disturb clots while performing thrombectomies, or clot removal procedures. Currently, for another project, we have a design shape, and the project is in a refining state where we need to experimentally derive at what density of bristles the morcellator performs best. And I will justify the step sizes used in the experiment for my optimization. So, some technical stuff. The diameter of the tube simulating the vasculature will be 15 millimeters, which is about the average diameter of the human inferior vena cava, which is kind of what we were simulating. The diameter of the inner catheter over which the morcellator will be deployed is 2 millimeters. That gives us a circumference for the morcellator at 2 pi, or about 6.28 millimeters. The bristles themselves are about 2 millimeters long and are 0.5 millimeters in diameter. Now the large particle filter size will be 0.1 millimeter holes, and the small particle filter size will be 0.005 millimeter holes. Basically what this serves to do is separate between large and small particles, where the large particles are anything larger than 0.1 millimeter, and the small particle filter serves to capture everything else. And this is because the use of a typical thrombectomy device has been shown to create upwards of 300,000 particles sized 10 to 100 picometers, 1,000 particles sized 100 to 1,000 picometers, and about 20 particles larger than 1 millimeter on average. Now this is important because while it may seem that large particles are more dangerous, actually the larger particles are easier to capture, while the smaller particles can do just as much damage and are harder to capture. And if they slip by the treatment zone and make their way into the lungs, that's what causes a pulmonary embolism, or one of the major side effects or bad things that could happen during a thrombectomy. So, the statistical justification for Morcellation density step size. Now, due to a lack of experimental data, I will have to rely on my a priori epistemological knowledge and Bayesian statistics. I impose an a priori belief that 6 bristles per band is the industry standard in terms of density, and that it also creates about equidistant bristles, because if the bristle is about half a millimeter and there's about 6 millimeters in the circumference of the morcellator, you get half a millimeter of bristle, a half millimeter of space, and then another bristle, which continues around the circle. Now, what we want to minimize is this mean squared error function, which is the mean minus the desired size squared plus the variance. The mean being the mean of the expected particle size created, and the desired size being the desired particle size of 0.1 millimeters, because it is easier to capture and less of a risk. Now, my a priori belief in variance. My a priori belief is that the maximum a posteriori, or MAP, estimate Bristol density of about 6 per band creates a normal distribution of particles created by size. We want to see a left-leaning or positively skewed, as well as a right-leaning or negatively skewed distribution. My hypothesis is that higher density bristles will create more smaller particles, which is bad, but will have less variance in performance, which is good. I also hypothesize that lower density bristles will create more of the desired larger particles more often, but will also come with a higher variance in performance. Additionally, in a lower density bristle morcellator, orientation may become prevalent, especially if the clot is stuck on one side of the treatment zone, which is very often the case. This introduces even more variance, which may offset the increased performance. So I will set my bristle density at 4 bristles per band, 6 bristles per band, and 8 bristles per band. And as you can see, I hypothesized the performance distribution below, where at 6 bristles, you see some kind of a normal distribution of particles created by size, which is the x-axis. And at a higher density of bristles, you will see an uptick of smaller particles created, but a decrease in variance of performance. And at 4 bristles, or a low density bristle morcellator, we'll see more of the larger particles that we want more on the right side, but an increased variance in performance, which is unfortunate. So, to the experiment itself. The first step is to create an artificial clot, usually with cherry jello, inside the flow model, sometimes strawberry. Once set, we'll remove the clot and weigh the clot to get the initial clot weight. Now, putting the clot back inside the model, we'll set up the morcellator and the device such that both the proximal and distal sides are completely occluded, which is basically the front and back end of the treatment zone. Step 3 will be to run the morcellator back and forth through its complete range of motion 3 times. This serves as the procedure. Step 4 is to drain out the flow model and remove any of the remaining initial clot, if there is any. This is where our one constraint comes into play, which is step 5, and we have to weigh the remaining clot and determine if the constraint of at least 50% removal by weight was met. If this constraint was not met, the trial and the morcellator is deemed a failure. If it is met, we can run the drained water through the large step filter, which serves to isolate the large particles created. Keeping the filter, we drain the remaining water through the small step filter, which captures basically the rest of the particles that aren't large. Step 7 and 8 is to weigh each filter, subtract the weight of the filter itself to get the weight of large and small particles created, respectively. Step 9 is where we find our objective function, or the numerical score, basically, for each morcellator, and that is by finding the ratio of weight of large particles created to the total weight of particles created, which is the sum of the large and small particles. By maximizing this ratio, we'll want to see the maximized performance of creating large particles versus particles created. Step 10 is to repeat the procedure 5 times per morcellator for consistency and to ensure that the data is replicable. So continuing on, my next step will be to prototype and create these morcellators either through 3D printing or some other kind of manufacturing, and run the very experiments, which I will do during the summer here at WashU with my fellowship at SINT. Variations of this experiment are also very attractive, where we can vary, instead of the number of bristles per band, we can vary the number of bands of bristles. So that is varying laterally along a cylinder instead of radially. Another variance we could do is to change it to the experiment to just the number of bristles per square area of morcellator. So instead of working in 1 dimension, we work in 2 dimensions. Another variation of the experiment could be to work with different shapes of bristles, not just straight columns like a pipe cleaner, but maybe as thin wires that'll kind of serve as cheese cutters to carve out the clot, which may perform better. Thank you. If you have any questions, please email me at my email at sally@wustel.edu. And thanks for a wonderful semester.